Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about F distributions, and we also do an example where we use them. By the way, these distributions, F distributions, are very important to carry out hypothesis tests in multiple linear regression. Okay, I just wanted to mention that. Let's begin. So here's the definition of an F distribution. Okay, so the ingredients that you need to construct an F distribution are two independent chi-square random variables. We're going to denote the first of them by W1 and the second of them by W2. Okay, so what you are going to be doing to come up with an F distribution is it's a ratio of these chi-square distributions divided by their corresponding degrees of freedom. Okay, so W1 is a chi-square distribution with nu 1 degrees of freedom, so W1 divided by nu 1 divided by W2 divided by its own degrees of freedom, W2. That quantity, that ratio, has an F distribution. Okay, so the degrees of freedom for the chi-square that is placed on the numerator, right, those are referred to as the numerator degrees of freedom. And well, similarly, right, the degrees of freedom for the chi-square placed in the denominator, well, you're going to refer to those as the denominator degrees of freedom. Next, let me show you a few graphs of the PDFs of different F distributions. So for instance, the black one is an F distribution with 3 degrees of freedom in the numerator and 5 degrees of freedom in the denominator. Okay. The green one, on the other hand, is an F distribution with 50 degrees of freedom in the numerator and 50 degrees of freedom in the denominator. Okay, so just bear in mind that these guys, one property of F distributions is that the support, right, the non-zero part of that PDF is the non-negative real numbers. Okay, and it has a relationship with other distributions such as the t distribution, right, and exponential distributions. And you can take a look at that here. Just a quick note about those relationships. Okay, so take a look at those later. But the most important part here is what I want you to remember is the definition of the F distribution. Okay, now at this point we're going to be using an F distribution to do inference, statistical inference, when variances are involved. Okay, so that's the application that we're going to be doing here, right? We want to do inference for variances. Now the conditions are the following. Okay, remember that what we said, I think it was when we discussed theorem 7.3, what we said is that if you have a random sample of size n coming from a normal with mean mu and variance sigma squared, then this quantity n minus 1 times the sample variance s squared divided by sigma squared has a chi-square distribution with n minus 1 degrees of freedom. Okay, now if you have another sample independent of the first one, also coming from a normal, right, the mean could be different, but we have a common variance here, right, then you could construct a similar quantity again, this is based on the result that we discussed in theorem 7.3, right? Now this guy, m minus 1, because we have a sample of size m in this case, m minus 1 divided by sigma squared, we have a common variance, right, times the sample variance for that new random sample, then this guy has a chi-square with m minus 1 degrees of freedom. Since these guys are independent, when we do that ratio, we divide that chi-square by its degrees of freedom, n minus 1, this chi-square by its degrees of freedom, m minus 1. Just by definition, that ratio has an F distribution with n minus 1 degrees of freedom in the numerator, m minus 1 degrees of freedom in the denominator. Make sense? So as you can see, that distribution will be useful to say something about variances, just by the very definition. So let's talk about that example. We're going to be doing this first part. You can take a look at the second part on your own, but it is going to be very similar, and the solutions are there in our lecture notes. So in this case, what we do is we're talking about we are talking about scores, marks, right? So and we assume that the random variable score or mark has a normal distribution with mean 75 and standard deviation 15. So that test, right, was given to two different classes, right, two different sections. And the first one had 31 students, the second one 16 students. And we want to say something about the variances, right? The ratio of the variances, to be more specific, right? So we want to do A, well, the sample variance of A divided by the sample variance of B. We want to compute the probability that that ratio of sample variances is greater than 2. Okay? So that's the ultimate goal. Okay? So let me write it down like this. What we want to compute, to find the following probability. Probability that the following ratio, let's call it S sub x, or yeah, let's call it sub a squared. And let me do it like this, because I'm going to need a subscript and a superscript. Okay, so we want to compute the probability that the ratio between those two variances is greater than 2. Agreed? That's what we want. Okay, so now that is not quite what we need, right? The thing is, it would be great if we had something that looks like sample size minus 1 times s squared divided by sigma squared, right? Now note that we're assuming that these two samples, let me call this guy sample A and sample B, come from the same distribution. So they have the same mean and the same standard deviation, right? Okay, but what is different is the sample size. So first, to make the quantity that we know the distribution of appear, what we do is this. Hey, note that this is the same as this divided by sigma squared. And if we divide the numerator and the denominator by the same quantity, what we're doing is we're just multiplying by a 1 deep down, right? So those two events are equivalent. Make sense? Okay, now what we're going to be doing is, hey, how about I multiply by a 1, and my 1 is going to be looking like this: n sub a minus 1 divided by the same quantity. So if I multiply and divide by that same quantity, then that's just a 1, right? Okay, let me do the same here. But now note that what we have is n minus 1 times s squared divided by sigma squared. We know that under the conditions that we have, because we are drawing observations from a normal, right? That by our theorem 7.3, this quantity here, n sub a minus 1 times s sub a squared divided by sigma squared, that has a chi-square distribution with na minus 1 degrees of freedom, and we're dividing that guy by its degrees of freedom. Okay, so let me rewrite what we have there, and we're going to have a similar situation in the denominator, right? Let me copy this and modify that slightly, right? So what we're going to have is, let me get rid of this. We're going to have a chi-square with n sub a minus 1 degrees of freedom and another way of referring to a chi-square with n sub a minus 1 degrees of freedom is just using a subscript. So let me use that subscript here. So degrees of freedom na minus 1, and then we're going to have a similar situation here for the denominator. Make sense? Right? So a chi-square divided by its own degrees of freedom. We have an independent chi-square because that one is based on an independent sample, right? So these two guys are independent. It's a ratio of two chi-squares divided by their respective degrees of freedom. So this guy has an F distribution with na minus 1 degrees of freedom in the numerator and f minus 1 and mb minus 1 degrees of freedom in the denominator, right? There we are. Make sense? Okay. So, in this particular case, what we have is first sample 31 students, So 31 minus 1, 30. 16 minus 1, 15 degrees of freedom. So what we want is the probability that an F distribution with 30 and 15 degrees of freedom is greater than 2. Okay? So first, let's try and do this using our table. Okay? So let me say that. Using table. So let's see, we have our textbook, and now we have to go to page 857, right? So we have 30. Well, first let me show you what that table looks like. First, take a look at that graph. This guy, that table from your textbook, is going to give you areas to the right. Okay? Okay. Now, in this case, we have 30 degrees of freedom in the numerator. So this first row here gives you that information, the degrees of freedom for the numerator, and that column here gives you the degrees of freedom for the denominator. Note that first row gives you the numbers that have 10% to its right, 5% to its right, 2.5% to its right, 1% to its right, and 0.005 to its right. Make sense? Okay. So let's find again 30 degrees of freedom for the numerator. That's what we want, and we want 15 degrees of freedom for the numerator. So 15 denominator, 30 for numerator, right? So now note that what we want is the probability that an F distribution is greater than 2. So we find something as close as possible to 2. This guy or this guy, right? So, and now we refer to that row here. It turns out the interpretation is, if you have an F distribution with 30 degrees of freedom in the numerator and 15 degrees of freedom in the denominator, to the right of 1.87 you have 10%. Same goes for 2.25. If you have an F distribution with 30 degrees of freedom in the numerator and 15 degrees of freedom in the denominator, the area to the right of 2.25 is 5%. So we don't have exactly 2, but we have this. So we can bracket 2 by these guys, and using our table, the best that we can do is, hey, the probability that we want, must be between 5 and 10%. Make sense? Now, let's do it using R. It's going to be really simple, and we're going to see that the result makes sense, right? I mean, it's not going to be using that table is not very accurate, but it's going to be correct. So if you want the CDF of an F distribution, meaning the cumulative distribution function of an F distribution, right? The function that you will be using is PF, okay? And then you need the number that you're interested in this case, hey, I want the probability to the right of 2, or the proportion of observations to the right of 2, right? But note that since R uses the CDF, you want to rewrite this like so. Probability that an F with 30 degrees of freedom in the numerator and 15 degrees of freedom in the denominator is greater than 2 is the same as 1 minus the probability that that F distribution is less than or equal to 2. Make sense? Now this guy is in terms of the CDF. Okay, so because if you just do this, right, what you're going to be getting, and remember the first one is going to be the degrees of freedom for the numerator, the second one is for the denominator. So if you just do this directly, what you have is the area to the left of 2, but you want the area to the right of 2, so you do 1 minus, and that's your guy. So 7.86% happens to be between 5 and 10%, right? So using your table, you're not going to be able most of the time to provide that exact probability, but you're going to be able to bracket that probability. Okay, makes sense? Okay, so let's summarize what we did here together. So what we were interested in this particular problem was saying something about the ratio between sample variances, right? And in this case, the conditions that we had were that we had two independent random samples coming from a normal distribution with a common standard deviation or common variance, right? So we realized that if you wanted to say something about that ratio of sample variances, we could use an F distribution just by the very definition of an F distribution, right? And definition is here, so you can see it. It's just the ratio between two chi-square distributions divided by the respective degrees of freedom. And by theorem 7.3, we know that n minus 1 s squared divided by sigma squared, if we have a sample coming from a normal, that quantity will have a chi-square distribution. And that's what we exploit. That theorem 7.3 in combination with the definition of an F distribution to solve our problem. Make sense? Okay. So, yeah, that's it. Thank you so much. Please take care and keep working hard. See you next time. Bye.